Most EV battery headlines in 2026 promise the same thing: solid-state breakthroughs, 5-minute charging, 400 watt-hours per kilogram, game-changing tech that supposedly makes everything else obsolete. But here's the part almost nobody stops to ask. If these batteries are truly ready, why are most real cars still shipping with lithium-ion? Today we're connecting the dots across the whole market. Donut Labs' extreme solid-state claims: aluminum-ion built for pure power, cheap sodium-ion quietly cutting pack costs, Geely still stuck at validation, and Tesla continuing to scale 4680 cells by the millions. Different chemistries, different trade-offs, different risks. And only one of them is actually showing up in factories every day. Because in the real world, batteries don't win on spec sheets. They win on production lines, cost per kilowatt hour, and how safely they survive 10 years of ownership. If you want analysis based on numbers and manufacturing reality instead of hype, you're in the right place. This is autogearshift. Hit like, subscribe, and turn on notifications. And let's break it down. Most people assume better battery specs automatically mean better outcomes for EV owners. Are you one of them? Because that's a false shortcut, and one the media rarely challenges. Donut Lab claims a solid-state battery with 400 watt-hours per kilogram energy density, full charge in about 5 minutes, and up to 100,000 charge cycles, already hitting the road in 2026 Verge TS Pro motorcycles, far beyond typical lithium-ion performance. But here's the part almost nobody asks. If a battery like this were truly production-ready and reliable, why isn't the rest of the industry adopting it? And why, despite these headline numbers, Tesla still builds its vehicles with 4680 cells that are proven at scale? Takations. We're closing in on 24,123 subscribers, and every new sub supports clear, data-driven breaking down of EV tech that others skip. Donut Labs Spec Shock. We will talk only what actually matters. Donut Lab claims its all-solid-state battery is already production-ready, not a lab prototype, not a pilot line. Here are the numbers that matter. The company claims an energy density of 400 watt-hours per kilogram at the cell level. For context, most high-end automotive lithium-ion cells today sit in the 250 to 300 watt-hours per kilogram range. On paper, that's a step change, not an incremental gain. Charging is where the claim becomes more aggressive. Donut Lab says the battery can go from empty to full in as little as 5 minutes, without limiting state of charge to 80%. That's a charging profile closer to fuel refueling than traditional EV behavior. Longevity claims are even more extreme. Donut Lab states the battery can endure up to 100,000 full charge cycles. By comparison, today's automotive-grade lithium-ion packs are typically engineered for 3,000 to 5,000 full cycles, often under conservative charging limits. Temperature tolerance is another standout. Donut Lab says its solid-state cells retain over 99% capacity in environments ranging from -30 degrees Celsius to 100 degrees Celsius. If accurate, that removes two of the biggest constraints in EV battery design: cold weather degradation and high heat safety buffers. Finally, Donut Lab claims gigawatt-hour scale production readiness today, using materials it describes as widely available and free from rare element supply constraints. No roadmap, no by 2030. The claim is simple. This battery exists, scales, and ships now. On paper, that's not just better than Tesla's 4680. It makes 4680 look outdated. But paper has never been where automotive batteries fail, and that's where the real test begins. Quick question before we go deeper. Comment 1 if you think specs this extreme mean the battery is the future and the industry is just slow to catch up. Comment 2 if you think when specs sound this good on paper, real-world risk usually shows up later, in cost, scale, or reliability. And let us know why you picked 1 or 2 in the comments. That reasoning is exactly where this story gets interesting. What Verge Motorcycles actually did with this battery. On paper, Donut Labs' solid-state battery looks disruptive. But Verge Motorcycles is where those specs touch reality. And that's where things quietly slow down. The Verge TS Pro, powered by Donut's solid-state battery, reports a city range of 217 miles, which is exactly the same as the previous version using a conventional lithium-ion pack. There is no sudden jump in daily usability, no dramatic change in how far most riders can go on a normal charge. Yes, Verge does offer a large battery option, fitted into the same physical cradle, pushing claimed range up to 370 miles. But that improvement doesn't come from unlocking some hidden efficiency miracle. It comes from putting more battery in, not fundamentally changing how the vehicle behaves. The most visible upgrade is charging. Charging time drops from roughly 35 minutes to under 10 minutes, even though Verge openly admits it intentionally slowed charging down so riders wouldn't feel rushed. That detail matters more than it sounds, because it tells us something critical. Even with a dramatically better battery, the OEM chose not to operate it anywhere near its theoretical limits. And that raises an uncomfortable question. If the battery truly delivers 400 watt-hours per kilogram, extreme cycle life, and near-instant charging, why does the real-world vehicle feel only incrementally better, not transformational? The answer isn't marketing. It's risk management. Motorcycles are lighter, lower volume, and face a very different warranty and thermal risk profile than cars. Verge can afford to move cautiously, gather data, and still benefit from faster charging as a headline improvement. But notice what they didn't do. They didn't redesign the vehicle around the battery. They didn't push range as the main selling point. They didn't let the battery redefine the platform, which suggests something important. A better battery doesn't automatically translate into a better product, especially when long-term reliability is still being proven. And if that's the case for a motorcycle OEM willing to take risks, why 4680 still makes sense in 2026? At first glance, Tesla's 4680 battery looks unimpressive next to Donut Lab's claims. The numbers simply don't compete. While Donut Lab talks about 400 watt-hours per kilogram, real-world measurements place current 4,680 cells roughly in the 240 to 280 watt-hours per kilogram range at the cell level, and closer to 160 to 200 watt-hours per kilogram once integrated into a structural pack. But that gap is exactly the point. Tesla did not design 4680 to win spec sheets. Tesla designed it to survive mass production. Battery performance only matters if it can be produced repeatedly, predictably, and cheaply. That's where 4680 starts to look far more dangerous than it seems. Current industry estimates place Tesla's 4680 cell cost at around $100 to $105 per kilowatt-hour, already close to the psychological threshold where EVs begin to undercut combustion vehicles without subsidies. More importantly, internal cost models suggest that as yield improves, Tesla could push that figure below $85 per kilowatt-hour, a level very few competitors can realistically reach with newer chemistries. This is not theoretical. Tesla has already produced millions of 4680 cells at Gigafactory, Texas. That matters, because in automotive manufacturing, scale is not just about volume, it's about yield. A battery technology only becomes viable when defect rates drop low enough to sustain near-continuous production above 90% usable yield. Early 4680 lines struggled, but successive design simplifications, fewer welds, fewer components, thicker electrodes, were specifically aimed at stabilizing that yield curve. And that stability compounds elsewhere in the vehicle. Because 4,680 cells are physically larger, a typical 100 kilowatt-hour pack needs hundreds fewer cells than older 2,170-based designs. Fewer cells mean fewer failure points, simpler thermal management, and faster assembly. When combined with Tesla's structural battery pack design, this reduces pack mass by roughly 20 to 25 kilograms and cuts overall pack cost by an estimated 5 to 7% without chasing extreme chemistry limits. Charging behavior reinforces the same philosophy. Tesla's vehicles are already capable of pulling 250 to 300 kilowatts on fast chargers, yet Tesla deliberately caps sustained charging rates to preserve long-term cell health. This is not a limitation of chemistry, it's a production decision. A battery that lasts longer and degrades predictably across millions of vehicles is more valuable than one that charges in 5 minutes, but introduces unknown aging behavior at scale. And then there's supply chain reality. The 4680 does not rely on exotic or unproven materials. Its cathode and anode inputs are already sourced globally at massive volume, with contracts designed to smooth geopolitical risk. That's not exciting, but it's exactly why Tesla can build cars every day, instead of promising breakthroughs that depend on supply chains that don't yet exist. This is the core misunderstanding many people have when comparing batteries. Tesla does not need the best battery in the world. Tesla needs the battery that shows up on time, at cost, at scale, millions of times in a row. That's why, despite all the noise around solid-state breakthroughs, the 4680 remains untouched at the center of Tesla's production strategy. Winning batteries don't win on specs. They win on factories. So what does the real question this raise? Once you step back from the specs, a different question starts to matter more than whether Donut Labs' battery works. If this solid-state battery is truly as transformative as claimed, double the energy density, ultra-fast charging, extreme durability, wide temperature tolerance, then the way it's being introduced into the market starts to feel unusual, because historically, breakthrough batteries don't debut quietly. When lithium-ion became viable, it immediately attracted consumer electronics giants. When high-nickel chemistries matured, automakers rushed to secure pilot lines. When LFP proved cheap and stable, it spread across entire vehicle segments in just a few years. Yet here, we're told a battery that could theoretically make most existing EV packs obsolete is first appearing in a low-volume electric motorcycle, built by a relatively small OEM. That choice raises questions. Motorcycles are far more tolerant of experimentation than cars. They face lower regulatory barriers, smaller warranty exposure, and dramatically lower total energy storage requirements. A technology that might be risky at automotive scale can survive far longer in a niche where failure costs are limited. So the question isn't whether Donut Labs' battery is impressive. The question is what it's optimized for. Is it optimized for energy density over long durations, like an automotive battery needs to be? Or is it optimized for high power delivery, rapid charge-discharge cycles, and thermal resilience, traits that matter far more in motorcycles, performance applications, or even non-automotive use cases? That distinction matters because batteries built to move energy quickly are not always good at storing energy efficiently for hours at a time. And batteries designed for extreme cycle counts don't automatically scale well when each pack must last 10 years across millions of vehicles. Which leads to another question. If this technology is ready for gigawatt-hour production, why haven't we seen pilot programs with major automakers? Why no limited-run automotive demos? Why no transparent third-party validation yet? None of these questions disprove the technology, but together they shift the conversation away from hype and toward risk. Because in the EV world, timing matters as much as chemistry, and being early can sometimes look exactly like being wrong. So for now, the takeaway is not that Tesla's 4680 is better, and it's not that Donut Labs' solid-state battery is fake either. The real difference is this. 4680 wins because it exists at scale. It shows up every day, inside real vehicles, backed by factories, yield data, and supply chains that already work. Donut Labs' battery, on the other hand, might represent something else entirely. Not a replacement for today's EV packs, but a signal of where battery development is splitting into different paths. And that's the part most people miss. Because the future of batteries may not be about one chemistry winning everything, but about different batteries solving different risks. Now here's the question I want to leave you with. Do specs matter more than production? Or does the battery that ships first always win? Solid-state batteries are being sold as the answer to everything. Faster charging. We looked at Donut Labs' solid-state battery claims. 400 watt-hours per kilogram, 5-minute charging, and a cycle life that sounds almost unreal. Solid-state batteries seem to be the answer to everything. Faster charging, longer life, fewer limits. But here's the part most headlines skip. What kind of work is this battery actually built to do? Because in the real world, EV batteries don't all play the same role. Some are designed to store energy efficiently and last for years. Others are built to dump power fast, survive heat, and work under constant stress. That's why in this video, we're not ranking batteries. We're separating energy batteries from power batteries, using Donut Labs' solid-state and aluminum-ion as the contrast. When fast charging hides the real trade-off. When people hear 5-minute charging, they instinctively assume one thing: power. They picture a battery that can absorb energy instantly and deliver it just as aggressively. But in battery engineering, those two things are often in tension, not alignment. Donut Labs' solid-state numbers point very clearly in one direction: energy retention and longevity. A claimed 400 watt-hours per kilogram is not about pushing current. It's about packing as much energy as possible into a given mass. That kind of design typically prioritizes dense electrode structures and stable interfaces, great for range and cycle life, but not automatically optimized for sustained high-power discharge. The same applies to the 100,000 cycle claim. Cycle life at that scale usually comes from limiting mechanical stress, heat spikes, and aggressive current swings inside the cell. In other words, the battery survives by avoiding extremes, not by living in them. That's exactly what you want in vehicles that charge often, discharge moderately, and repeat the process for years. Even the 5-minute charging claim fits this pattern more than it appears. Fast charging does not necessarily mean continuous high-power output. Many batteries are engineered to accept short, intense energy bursts during charging, while still being conservative on discharge to protect internal structures over time. So when Donut Lab positions its solid-state battery as fast charging and ultra-long-lasting, the message isn't, "This battery does everything." The message is more subtle. This battery is extremely good at holding energy, surviving repetition, and staying stable, not at acting like a constant power pump under heavy industrial load. And that distinction matters, because the moment you ask a battery to deliver sustained high power, in heat, under load, without rest, you are no longer testing energy density. You're testing whether it's a power battery at all. That's where the comparison starts to shift. What aluminum-ion is actually built for? If Donut Labs' solid-state battery is obsessed with how much energy you can store, aluminum-ion batteries are built around a different obsession: how fast energy can move without breaking the system. Start with the number everyone ignores: power density. Most aluminum-ion cells reported in peer-reviewed research operate comfortably at 10C to 20C continuous discharge, with demonstrated pulse discharges reaching 50C to over 100C in controlled setups. That means the battery can deliver its full stored energy in minutes or seconds without structural damage. Now compare that to automotive lithium-ion. Even high-performance EV cells are typically designed for 2C to 3C continuous discharge, with higher bursts only allowed briefly before thermal throttling kicks in. The limitation is not software. It's chemistry, heat generation, and electrode stress. This is why aluminum-ion batteries look underwhelming on a range chart, but suddenly become unbeatable in machines that never stop working. Energy density tells the opposite story, and deliberately so. Aluminum-ion cells usually land between 40 and 70 watt-hours per kilogram, with optimistic lab demonstrations pushing toward 90 to 100 watt-hours per kilogram. That's a fraction of lithium-ion, and nowhere near Donut Labs' claimed 400 watt-hours per kilogram. But lower energy density also means less internal heat per unit of power delivered. You're not cramming massive energy into a tight structure. You're spreading it out, which dramatically reduces thermal stress during rapid charge and discharge. That's why aluminum-ion systems can operate in environments where cooling is minimal, passive, or non-existent. Cycle life numbers look confusing until you understand what kind of cycle is being measured. Aluminum-ion batteries are not optimized for deep, slow, 0 to 100% energy cycles. Instead, they excel at high-frequency microcycles: charge, dump, recover, repeat. Many studies show 20,000 to 50,000 cycles with minimal degradation under high-rate conditions, precisely the pattern seen in industrial and grid-adjacent systems. This matters because real machines don't behave like personal cars. A port crane, mining vehicle, or grid stabilizer might cycle its battery hundreds of times per day, but only across a small state of charge window. Lithium-based energy batteries hate that. Aluminum-ion doesn't. Thermal tolerance pushes the divide even further. Aluminum-ion chemistry remains stable well above 60 to 80 degrees Celsius, temperatures at which most EV battery packs are already deep into performance derating or active cooling dependency. In hot climates or sealed industrial environments, this difference alone can determine whether a battery is usable at all. And this explains the pattern we keep seeing in deployment. Aluminum-ion batteries show up in heavy industrial equipment, grid buffering and frequency regulation, rail and port systems, regenerative braking capture systems. Not because they're cheaper, not because they're more advanced, but because they can absorb abuse without changing behavior. So when you place aluminum-ion next to Donut Labs' solid-state battery, the conclusion isn't that one is behind the other. It's that they answer completely different questions. For Donut Lab, it's how much energy can we store, how safely and for how long. For aluminum-ion, it's how fast can energy move, how often and under how much stress. And once you see that, the real issue becomes obvious. Comparing these batteries directly is like comparing a fuel tank to a hydraulic pump. They don't compete. They coexist, as long as you put them in the right job. The risk no one talks about, using the wrong battery for the wrong job? This is where the real risk shows up, not in the chemistry, but in the assumptions. When people hear 5-minute charging and 100,000 cycles, it's easy to assume a battery like Donut Labs' solid state should work everywhere. Passenger cars, heavy trucks, industrial machines. Why not just use the best battery for everything? Because batteries don't fail when they're bad. They fail when they're misused. High-energy batteries, by design, prioritize energy retention over power delivery. Packing 400 watt-hours per kilogram into a compact structure means tighter electrodes, higher internal energy concentration, and stricter thermal boundaries. Even if a solid-state electrolyte reduces fire risk, it does not eliminate mechanical and thermal stress under sustained high load. This is why fast charging does not automatically translate to high continuous discharge. A battery that can absorb energy extremely quickly is not necessarily optimized to dump energy continuously at high power. Those are two different stress profiles. One stresses ion transport during charging. The other stresses heat dissipation, electrode stability, and structural fatigue during discharge. This distinction becomes obvious in industrial duty cycles. Consider equipment that operates at near constant load: construction machinery, port vehicles, mining equipment, or grid-connected systems. These machines may draw high power for hours, not seconds. Even brief thermal throttling in those environments isn't an inconvenience. It's a failure mode. This is where aluminum-ion batteries quietly outperform energy-dense alternatives. Because aluminum-ion systems are designed around power throughput, not energy packing, they tolerate sustained high currents with far less derating. Lower energy density means lower heat accumulation per unit of power delivered, which allows the system to behave predictably under abuse. The risk isn't that Donut Labs' battery can't handle power. The risk is assuming it should, and this matters for OEMs more than consumers realize. Designing a vehicle or machine around the wrong battery type forces compromises everywhere else. Larger cooling systems, conservative power limits, software throttles, and shortened service intervals. On paper, the battery still looks revolutionary. In practice, the system becomes fragile. This is why we don't see Donut Labs' solid-state battery debuting in heavy industrial platforms. Not because it isn't impressive, but because its strengths don't align with those workloads. So the real takeaway isn't that aluminum-ion is better or solid-state is not ready. It's that modern battery design has become specialized, whether the marketing admits it or not. And once batteries become specialized, the question changes. It's no longer, which battery is the best? It becomes, which battery fails most gracefully when pushed beyond its comfort zone? And that's a question spec sheets never answer. So where Tesla actually uses these batteries? To understand where these batteries realistically fit, we need to look at Tesla's scale, not theory. In 2024, Tesla delivered roughly 1.8 million vehicles globally. Internal targets and analyst estimates point to 2.2 to 2.5 million vehicles per year by 2027. At that scale, Tesla consumes on the order of 150 to 180 gigawatt-hours of batteries annually just for vehicles. That number alone filters out most breakthrough batteries. For a new chemistry to matter to Tesla, it doesn't need better specs. It needs tens of gigawatt-hours of stable output year after year. If Donut Labs' solid-state battery were production-ready today at meaningful scale, even a 5 gigawatt-hour annual line would only cover about 3% of Tesla's current demand. That's not disruption. That's a pilot program. And that's why solid-state in the near term fits better in sub-10,000 unit vehicle programs, not mass-market EVs. Now look at aluminum-ion through the same lens. Tesla's passenger vehicles typically draw 20 to 40 kilowatts during steady highway driving, with brief spikes during acceleration. Aluminum-ion batteries are optimized for high continuous power output, often 5 to 10 times higher C rates than energy-focused cells, but at the cost of energy density, often projected below 100 to 150 watt-hours per kilogram at the pack level. If Tesla used aluminum-ion in a Model Y-sized vehicle, the pack mass would increase by 40 to 60% for the same range. That's not a trade Tesla will ever make for consumer vehicles. But shift the context to Tesla Energy. Tesla's Megapack systems routinely handle megawatt-scale power spikes, sometimes cycling multiple times per day. In that environment, energy density matters far less than cycle durability, thermal stability, and charge-discharge speed. Analysts estimate that even a 5 to 10% aluminum-ion penetration into grid-scale buffering could reduce lithium-ion stress and replacement rates significantly, without ever touching a single car. So, the future path looks less revolutionary than headlines suggest. By 2026 to 2028, solid-state batteries could realistically appear in low-volume, premium EVs, possibly motorcycles, possibly specialty vehicles, where fast charging and longevity justify higher costs and lower volumes. Aluminum-ion, if it matures, is far more likely to appear off-vehicle, grid buffering, fast response storage, industrial energy systems, and Tesla will continue doing what it always does. Stick with lithium-based cells, including 4680, until a new battery can prove not that it's better, but that it can show up at 100-plus gigawatt-hours scale without surprises. That brings us to the real tension in this series. If solid-state batteries aren't ready to scale for cars, and aluminum-ion isn't meant for cars at all, then what problem does Tesla actually still need a new battery to solve? That's the question we'll tackle next. Solid-state batteries get all the attention because they promise better performance. But here's the number that actually matters. Over 70% of EV buyers still cite price as the main reason they don't switch, not charging speed or battery life. Right now, solid state doesn't meaningfully lower vehicle cost. Sodium-ion does. Analysts estimate sodium-ion cells can be 20 to 30% cheaper than lithium-based batteries, with more stable raw material pricing. At the vehicle level, that's the difference between an EV staying above $30,000 or finally dropping below it. What solid state actually fixes? Solid-state batteries are built to fix engineering limits, not pricing limits, and the numbers make that clear. From a technical standpoint, solid-state solves real problems. Removing liquid electrolytes reduces fire risk and allows higher charge rates without aggressive cooling. That's why many solid-state programs target 3 to 5 times faster charging and operating ranges from -30 degrees Celsius to 80 to 100 degrees Celsius, compared to conventional lithium-ion packs that start losing performance below freezing and require thermal throttling above approximately 60 degrees Celsius. Cycle life is another area where the gap looks massive on paper. Most automotive lithium-ion packs today are engineered for roughly 3,000 to 5,000 full cycles, translating to about 300,000 to 500,000 miles in real-world use. Solid-state claims often project 20,000 plus cycles, and in extreme cases far more, far beyond the usable life of the vehicle itself. But here's where the market reality breaks the story. In 2025, battery packs still make up roughly 30 to 40% of the total cost of a mass-market EV. For a $35,000 vehicle, that's about $10,000 to $14,000 just for the battery. Early solid-state manufacturing is expected to push cost per kilowatt-hour higher, not lower, due to lower yields, new equipment, and stricter quality control. Even optimistic projections place early solid-state cells 20 to 50% more expensive per kilowatt-hour than mature lithium-ion lines. That means a solid-state upgrade doesn't reduce the sticker price, it increases it. And that's why solid-state doesn't change buyer behavior today. A 5-minute charge sounds revolutionary, but for most drivers charging at home overnight, the difference between 25 minutes and 10 minutes on road trips doesn't justify a $3,000 to $5,000 higher vehicle price. Solid state makes EVs better machines. It does not make them easier to buy. So let me ask you, if you were shopping for an EV today, what would actually change your decision? Comment 1 if better battery tech would convince you, even at a higher price. Comment 2 if a lower price matters more than specs. Tell us why in the comments. If you've made it this far, that probably means this kind of analysis actually works for you. So don't disappear after this video. Hit subscribe and turn on notifications so you keep getting breakdowns like this. The kind that question hype, timing, and real-world risk. We're closing in on 23,456 subscribers, and if you're still watching, you might as well be part of the group that cares about what really moves the market. Now, let's continue. Why affordability is the real battlefield. When people hear solid state, they instinctively think next-generation EVs, longer range, faster charging, fewer compromises. But once you put real 2025 sodium-ion data next to those claims, something interesting happens. Sodium doesn't try to win on range. It wins on system economics and reliability. Let's start with the numbers that actually exist today, not 2030 slides. In 2025, second-generation sodium-ion cells from large manufacturers like CATL are reaching 160 to 175 watt-hours per kilogram at the cell level. That's still below high-end lithium-ion, but it's no longer a toy number. In practical terms, that translates to 350 to 450 kilometers real-world range in a compact EV, enough for daily commuting, urban fleets, delivery vans, and secondary household cars. Now compare that to solid-state batteries like Donut Labs claims. On paper, 400 watt-hours per kilogram sounds revolutionary, but higher energy density creates secondary costs, stronger cooling requirements, tighter charging control, higher failure consequences, stricter manufacturing tolerances. Sodium-ion goes in the opposite direction. Because sodium chemistry is far more thermally stable, manufacturers can design simpler battery packs. Less cooling mass, less safety buffering, less software overhead. In 2025 estimates, sodium-ion packs are projected to cost $60 to $80 per kilowatt-hour, roughly 30 to 40% cheaper than lithium-based alternatives at the pack level, not cell level. That matters more than range for most buyers. Think about how cars are actually used. The average driver doesn't exploit 600 kilometers range. They exploit predictability, predictable winter behavior, predictable charging time, predictable degradation. This is where sodium-ion quietly outperforms expectations. In cold climates, sodium-ion batteries retain significantly higher usable capacity at sub-zero temperatures compared to lithium-ion. Real-world testing shows less voltage collapse at minus 20 degrees Celsius, which means fewer range surprises in winter. Something solid-state still hasn't proven at scale. Charging is another misunderstood area. Sodium-ion batteries in 2025 can already handle 15 to 20-minute fast charging, 0 to 80%, without aggressive thermal throttling. That's not 5 minutes, but it's repeatable day after day without pushing the cell into edge case stress zones. Solid-state fast charge demos, by contrast, often rely on controlled lab conditions, lower C-rate repetition, or undefined degradation trade-offs. 5 minutes sounds great once. Fleet operators care about what works 10,000 times, not once for a press release. Cycle life reinforces this gap. Sodium-ion batteries are targeting 3,000 to 6,000 full cycles in real-world duty. That's enough for 10 to 15 years of daily driving, even with frequent fast charging. And because sodium doesn't depend on lithium, cobalt, or nickel, supply volatility risk is dramatically lower. Solid-state batteries promise tens of thousands of cycles, but that advantage only matters if the battery is being deeply cycled, something private passenger vehicles rarely do. This is why sodium-ion adoption in 2025 is accelerating not in luxury EVs, but in entry-level city cars, ride-hailing fleets, delivery vehicles, grid-linked mobility systems. In these use cases, cost per kilometer matters more than peak energy density. So here's the uncomfortable truth solid-state marketing avoids. A battery doesn't need to be revolutionary to reshape the EV market. It needs to be cheap, boring, and predictable at scale. And in 2025, sodium-ion checks more of those boxes than solid-state does. Why sodium-ion moves EV markets faster than solid-state ever could? From 2025 onward, the EV market is no longer constrained by whether batteries can deliver more range. It is constrained by whether manufacturers can ship acceptable EVs at prices normal buyers will actually pay. That change in constraint is exactly why sodium-ion moves faster than solid-state. By late 2025, global sodium-ion production capacity is projected to exceed 100 gigawatt-hours annually, driven primarily by CATL and several Chinese Tier 1 battery suppliers. These are not pilot lines or demonstration plants, but industrial-scale facilities designed for continuous output. In contrast, solid-state battery capacity over the same period is expected to remain below 5 gigawatt-hours worldwide, with most output coming from semi-commercial or validation stage production. This gap matters because battery cost does not decline when chemistry improves on paper. Cost declines when factories run stably. Sodium-ion cells are inherently more tolerant to manufacturing variability. They require less aggressive moisture control, simpler electrode materials, and more forgiving formation processes. As a result, early sodium-ion production lines are achieving first-pass yields that are estimated to be 10 to 15 percentage points higher than those seen in next-generation lithium or solid-state lines at comparable maturity. Higher yield is not a technical footnote. It directly determines whether a battery program survives contact with financial reality. Now place that manufacturing advantage into the context of vehicle pricing. Between 2025 and 2027, the fastest-growing segment of global EV demand sits below the $25,000 price threshold. At that level, buyers are not cross-shopping kilowatt hours. They are deciding whether an EV is affordable at all. In this segment, a reduction of $2,000 to $3,000 in battery cost can determine whether a vehicle reaches mass adoption or remains a compliance product. This is where sodium-ion quietly reshapes EV strategy. With projected pack-level costs in the $60 to $70 per kilowatt-hour range, sodium-ion allows automakers to either lower vehicle prices directly or protect margins while absorbing rising costs elsewhere in the vehicle, such as safety systems, software, or regulatory compliance. Solid-state batteries move economics in the opposite direction. Even optimistic forecasts place early solid-state packs above $120 per kilowatt-hour well into the late 2000s, which confines them to premium or experimental vehicles with limited volume relevance. This distinction becomes especially important when we look at Tesla. Tesla has never won by adopting the most advanced battery first. It has won by deploying batteries at scale, with predictable cost and stable supply. Historically, Tesla only integrates new battery technologies once they improve cost per vehicle, reduce manufacturing risk, and strengthen supply chain control simultaneously. Solid-state batteries currently fail all three conditions. Sodium-ion aligns with them. A sodium-ion pack in the 45 to 55 kilowatt-hour range can deliver roughly 350 to 400 kilometers of real-world range, which is more than sufficient for urban commuters, second-car households, rideshare fleets, and autonomous mobility platforms. For a future Model 2 class vehicle, that trade-off makes strategic sense. It allows Tesla to reserve high-energy lithium packs for long-range and performance variants, while deploying cheaper, more abundant chemistry, where energy density simply does not matter as much. There is also a geopolitical layer that cannot be ignored. Sodium-ion batteries rely on widely available materials that are far less exposed to lithium mining bottlenecks and price volatility. For a manufacturer operating at multi-million vehicle scale, supply predictability often outweighs marginal gains in energy density. A battery that ships reliably every quarter beats a better battery that ships inconsistently. This is why sodium-ion does not need to outperform solid-state to win relevance in EVs. It only needs to arrive at the right moment. And that moment is now, while the market is still fighting price ceilings rather than range anxiety. Solid-state batteries may eventually dominate niches that demand extreme endurance or energy density. But EVs are no longer niche products. They are mass-produced transportation tools governed by cost curves and factory throughput. And in that environment, sodium-ion does not just compete with solid-state. It shortens the window in which solid-state makes sense for mainstream EVs at all. Here's what really matters if you're thinking like a buyer, not a spec watcher. Every time a next-gen battery appears, early adopters take the risk, not the automaker. And when that technology turns out to behave differently in the real world, it's owners who pay through depreciation, range redefinitions, or resale shock. Sodium-ion reduces that risk by being boring, cheap, and predictable. Solid-state increases it by being new, fast-moving, and still undefined at scale. And that leads to the next problem no one wants to ask yet. If Donut Labs battery charges in minutes and survives extreme abuse, is it really a traditional solid-state battery? Or is it starting to behave like a supercapacitor with an energy disguise? That's the real test facing Donut Labs tech, and that's exactly what we'll break down in the next video: solid-state or supercapacitor. The real test facing Donut Labs battery. Stay with autogearshift. Solid-state batteries are being framed as the next big turning point for electric vehicles, and 2026 keeps showing up as the year everything supposedly changes. Geely now says its self-developed solid-state battery will reach full pack completion and vehicle-level testing by then. But what does that actually mean in the real world? Does this move lower costs, reduce ownership risk, or change what buyers should expect over the next few years? And just as important, where does this leave Tesla? A company that continues to scale lithium-ion production instead of chasing solid-state headlines. Is Tesla falling behind? Or is it deliberately avoiding a technology that still doesn't make economic sense at volume? What does vehicle-level validation really mean for Geely in 2026? When Geely says its solid-state battery will reach vehicle-level validation in 2026, it sounds like a major leap forward. But in reality, that phrase carries a very specific and often misunderstood meaning inside the auto industry. Vehicle-level validation does not mean mass production, commercial readiness, or cost viability. It means the company has progressed beyond laboratory cells and is now assembling a complete battery pack, installing it into a test vehicle, and evaluating how that system behaves under real-world operating conditions. This step matters because it is the first time a solid-state design is exposed to the full set of stresses a production vehicle creates: vibration, thermal cycling, charging variability, structural integration, crash safety, and long-duration degradation. A laboratory cell that reaches around 400 watt-hours per kilogram, which Geely has reportedly achieved at the experimental level, is operating in a controlled environment. Once that cell becomes part of a pack, with cooling hardware, structural elements, wiring, and safety systems, the effective energy density drops, and new failure modes emerge. That gap between cell performance and pack-level reality is where many battery programs slow down or quietly reset expectations. In Geely's case, the 2026 milestone is about learning, not scaling. Completing a full pack and validating it in a vehicle allows engineers to measure how solid electrolytes behave over thousands of kilometers, how fast charging impacts thermal stability, and whether the pack can survive real-world duty cycles without abnormal degradation. It's also important to understand what Geely has not disclosed. The company has not confirmed which vehicle platform will host the test pack, how many validation vehicles will be built, or how long the testing phase will last. Seen in that context, Geely's announcement places it squarely in the middle of China's broader solid-state development timeline, not ahead of it. Other manufacturers are targeting similar validation windows, with most commercial ambitions clustered closer to 2027 or later. The significance of Geely's 2026 target is not that solid-state batteries are arriving, but that the company is positioning itself to understand the limits of the technology early, before committing capital to factories, tooling, and supply chains that may not yet make economic sense. If solid-state isn't ready, why does Tesla still bet on lithium-ion at scale in 2026? As Geely and other automakers move solid-state batteries into vehicle-level validation, Tesla's decision to double down on lithium-ion technology can appear conservative, but when viewed through the lens of cost, manufacturing scale, and ownership risk, the strategy becomes easier to justify. By 2026, lithium-ion batteries, particularly lithium iron phosphate, operate on a production curve that solid-state systems have not yet approached. At the pack level, LFP batteries used in mass-market EVs are widely estimated to sit well below early solid-state cost projections. While solid-state developers often highlight experimental cell energy densities around 400 watt-hours per kilogram, those figures do not translate directly to pack economics. A typical LFP pack in 2025 to 2026 operates closer to 150 to 170 watt-hours per kilogram, but it does so at a cost structure optimized across millions of units. By contrast, solid-state packs in validation phases still require specialized materials, low-yield processes, and slower assembly speeds. all of which drive pack-level costs significantly higher despite superior cell metrics. Tesla's 4680 cell program reinforces this cost-focused approach. The 4680 design reduces the number of cells per pack by a large margin compared with earlier cylindrical formats, simplifying electrical connections and pack assembly. When combined with structural pack integration, the battery becomes part of the vehicle's load-bearing structure, eliminating redundant components and reducing total material usage. These changes do not dramatically increase range on paper, but they lower cost per vehicle and improve manufacturing efficiency, advantages that scale directly with volume. To put this in practical terms, a mass-market EV priced in the $25,000 to $35,000 range cannot absorb a battery pack that carries a significant cost premium, regardless of energy density. Even a difference of a few $1,000s per pack can determine whether a vehicle program is profitable or not. Tesla's continued reliance on lithium-ion chemistry allows it to push pricing downward incrementally while maintaining predictable margins. There is also a reliability and warranty dimension that often gets overlooked. Lithium-ion degradation behavior over hundreds of thousands of kilometers is well characterized, and Tesla has years of fleet data to support long-term durability models. For an automaker selling vehicles at scale, uncertainty in long-term performance translates directly into financial risk through warranty claims and residual value impacts. This is why Tesla's competitive advantage in 2026 is not about having the most advanced battery chemistry, but about controlling variables that directly affect ownership experience. A slightly heavier pack with known performance, stable supply chains, and mature manufacturing processes often delivers more real-world value than a lighter, denser pack that is expensive and unproven at scale. By continuing to refine lithium-ion technology, Tesla positions itself to benefit immediately from cost reductions and production efficiencies, rather than waiting for solid-state batteries to clear economic and manufacturing hurdles. What do solid-state batteries in 2026 actually change for EV pricing, ownership risk, and buyers? For most EV buyers, the real question surrounding solid-state batteries in 2026 is not whether the technology works, but whether it changes anything meaningful at the point of purchase. Based on where development timelines currently stand, the answer is more restrained than the headlines suggest. From a pricing perspective, solid-state batteries in 2026 are unlikely to appear in high volume. Price-sensitive vehicles. The economics simply do not line up yet. Even if a solid-state pack achieves higher energy density at the cell level, the additional costs associated with specialized materials, low manufacturing yields, and slower production rates push pack-level pricing beyond what mainstream EV programs can support. For vehicles competing in the $30,000 range or lower, battery cost remains the dominant factor, and lithium-ion chemistry continues to outperform solid-state on that metric by a wide margin. Ownership risk tells a similar story. Lithium-ion batteries, particularly LFP packs, benefit from years of real-world data covering degradation, thermal behavior, and failure modes. This data underpins warranty structures, resale value forecasts, and insurance assessments. Solid-state batteries, by contrast, are still building that data foundation. Even after vehicle-level validation, manufacturers need years of fleet exposure to confidently model long-term performance. Until then, early deployments, if they occur at all, are more likely to be limited, controlled, and priced accordingly. There is also the question of where solid-state batteries would realistically be used first. In most cases, early adoption favors higher-margin vehicles, limited production runs, or technology demonstrators rather than mass-market models. These deployments prioritize learning and brand positioning over cost efficiency. For everyday buyers, that means solid-state technology is more likely to be something they read about than something they can actually purchase at an accessible price point in the near term. This gap between technological progress and consumer impact has implications for the used EV market as well. When a new battery technology is perceived as the future, it can create uncertainty around existing models, even if those models remain technically sound. However, if solid-state batteries do not reach meaningful scale until several years later, lithium-ion vehicles sold in 2026 to 2028 are unlikely to experience immediate depreciation pressure solely due to battery chemistry. Practical factors such as range adequacy, charging infrastructure, and reliability will continue to dominate resale values. As 2026 approaches, the contrast between Geely and Tesla becomes clear. Geely is using solid-state batteries as a long-term learning investment, pushing the technology into vehicle-level validation to understand its limits before committing to scale. Tesla, on the other hand, is competing by refining lithium-ion systems it already knows how to build, service, and price efficiently. One strategy is about preparing for what comes next, while the other is about winning in the market that exists today. What do you think? Do you see Geely's approach as forward-looking caution? Or do you think Tesla's focus on scale gives it a lasting edge? Let us know in the comments. And if this analysis helped cut through the hype, don't forget to like the video, subscribe to AutoGearshift, and turn on notifications so you don't miss our next deep dive into where the EV market is really headed.